Previously, we were looking at evaluating line integrals of scalar fields. In this video, we want to do the same thing. However, we're going to be looking at vector fields. So we'll be using vector fields. So first, I just want to go over briefly what we mean when we say a vector field. So like with scalar fields, we can look at R2 and also R3, but again, they're very similar. So let's look at R2. So in R2, we will recognize a vector field because we'll see something like this. We'll have a vector function here. We'll call it capital F. And we'll use two variables since we're in R2, x and y. And that's going to be equal to a function p with x and y, comma, another function q of x and y. So here, what makes this a vector function is that we don't just have one function, we have multiple. So in this case, in R2, we'll have a function p and a function q. What does this mean? Well, this is equivalent to just saying the function p of x and y multiplied by the unit vector I. And we're adding to that the function q at x and y. And since we're in R2, we will just leave it as this. We have the unit vectors I and j. I'm going to talk about a little bit later what this means and how we can kind of visualize it. But for now, just remember that that's the general form for an R2 vector field. Now, we can also look at R3, which is not really that much different. The only difference is we're going to add that extra variable z. So we'll have x, y, and z in our capital F function. And we will still have a vector function, but we're going to have one more. So we'll have the function p with all three variables. We will have a function q. And we'll also have a function r, for example. And again, all these functions are arbitrary. They could be any kind of function as long as they at most only have these three variables. So there's the difference with R2 and R3, and of course I can just write here to make the point clear. This is also equal to just saying the function p with the unit vector I, adding to that the function q, and that would be in the unit vector j direction, and finally we have the final direction, r, in the k direction, in the unit vector k. And so that's the general form for vector fields in both R2 and R3. Now, to help visualize this, you can imagine how a vector field works something like this. So we have the vector field function, and this is usually seen as a capital F. It's either going to be bold if you might be looking at like a question from a textbook, but if we're doing it by handwriting, you could just use the arrow on top to denote it's a vector because we have multiple components to it. Now that vector field function inputs a point. So we want to input some point x, y, and z. Now obviously if it's R2, we'll just only have x and y. If it's R3, we'll have x, y, and z. But in the most general sense, we'll use all three variables. So in a region we're talking about in some sort of space, we're going to pick a point with coordinates x, y, and z, put that into the vector field function, and what we get out of it is actually going to be, we are going to output a vector, which would, of course, be the function f evaluated at the point we inputted, x, y, and z. And the important thing here is that it's based at that point. it's at that point. So what does that mean? Hopefully it's coming together and you can visualize this. But essentially, if we're thinking about a cube, for example, at every point in that cube, we'll have a distinct coordinate, and this vector field will tell us that at each of those points, what is the magnitude of the vector and what's the direction that it's pointing into. So a very common example of this is if we think about a force field, for example. If we have a force that's given by a vector field function, we can think about it as, depending on where our position is in that cube or in that region, what's the force acting on us, what's the strength of the force, and in what direction is it acting. And we'll see in an example after this about a common application for these types of line integrals with calculating the work done by a force. But we'll look at that in a video. So now I want to go over the actual line integral portion of this. So we're going to look at the line integral, of a vector field. Now this is very similar to a scalar field, but there are some key distinctions just to keep in mind. And they do make a lot of sense because the difference here is now we're talking about a direction and not just a magnitude. Now, once again, we're going to just focus on R2, but again, this can very easily be extended to R3 just with the introduction of the other variable. So, and we'll see that in an example as well using R3. But for our purposes, we'll look at R2 just to keep it simple as we're learning it. So in general, a question would look something like this. So we'll have the line integral of C, then we'll have the vector function f with the input x and y, and then we'll dot that, we'll do the dot product with d lowercase r. I'll explain what that dr means, but I want to go like piece by piece. So let's just recap here. This is going to be an R2 vector field, because we have the two variables there, an R2 vector field. I want to talk about C first, and then we'll go back to the dr portion. So here, like with the scalar field, we have C that's going to be given by another vector function, that's the lowercase r, and it's going to have the two components, x of t, and the second component, y of t. And we're going to have that for t starting at A and going until B. So now you might realize this is pretty much identical to what we talked about with scalar fields, and it really is. Because in this case, C is still going to be some sort of curve, but again, we want to write it parametrically. So that's the same thing we're doing here. We're introducing the parameter t, and we want to create a function. We want to create two functions, rather, that represent the x values and the y values. And of course, we need to have the t bounds. We don't want the bounds to be in terms of x or y. We need it to be in terms of t. Now again, just to make another point, just like with the scalar fields, the exact parameter or the exact way in which we describe C parametrically doesn't matter. I could have something different than you and the line integral would end up being the same. However, we have to make sure that with the different combinations of x and t's and y of t's, we're still going to get the same curve C and in the same orientation. That's important, especially if we're going to look at applications where a plus or minus can actually mean something completely different. So now that we see that C part, let's look at dr. So here, what does the dr mean? Well, this r that we're talking about in the dr is the same r that we are describing C using. But let's just think about this. So if we consider dr dt, we all know what this means. This is the vector function r, and we are differentiating all of its components with respect to t. Now we'll just do simple rearrangement, and we'll find that, well, dr should equal r prime of t dt. And this is actually very similar to what we were looking at with scalar fields when we were looking at dx and dy. And it's the same idea that we're doing here. Now, just to make it very clear, what do we mean by r prime of t? Well, it's a vector function r of t, and all we're doing is we are taking the derivative of all of its components. So x of t and y of t. So that came from the curve C. So we made sure that C is given to us parametrically, and then once we have those components, we want to take the derivative of each of those components. And we're doing the dot product between those derivatives of the components and the vector field. Now let's see how we are actually going to evaluate this. So just like with scalar fields, computing a line integral as it is a bit tricky. So to help us, we want to convert it first into a definite integral, and then it becomes much easier to solve. So let's see how we do that. So again, we'll have some sort of general line integral here. So we have a general line integral here with f at x and y. We dot it with dr. And what does this mean? So let's write down the definite integral. So we have our bounds. We just talked about them, a and b. We have the same function f, but we're not going to just evaluate it at x and y. We want to evaluate it at the functions or the components of c that we have, x of t and y of t. This is just like what we did with scalar fields. Now the difference here is now once we have that, we want to dot it with r prime of t dt. And this should make a lot of sense to you, because if we didn't dot it, we'd have a function and we wouldn't get one answer. We would have some sort of vector perhaps as the result, or it might even be something more complex than that. But when we dot it, remember when you dot two vectors together, you're going to end up with a scalar value, and then we can easily take the definite integral from a to b with that. So let's just make this very clear. This here is now a definite integral. It's a definite integral with respect to t, that new variable. Now, usually when we do a question, this is going to be good enough for us. We can use this form and we can quite easily and nicely solve the question. But there is another form that you might see, or it might be useful in some cases. So we'll take a look at that quickly. So there's an alternate form. An alternate form. It's really the same thing, but it's a different way of thinking about it. So again, we're going to just take some arbitrary vector function x and y. And like we talked about at the beginning of the video, this could be some function p of x and y as the first component, and then q of x and y as the second component. So far, nothing new here. Now, something here interesting to think about is when we were talking about dr, we already said that's just the derivative of that lowercase r vector function dt. So what is this? Well, simply this is just going to be the derivative of all the components. Again, nothing new here. We just talked about this. But now, notice something interesting here. What is x prime of t dt and y prime of t dt? Let's think about x prime of t dt. Well, if you remember, we were looking at this a lot in the previous videos and in the video earlier in this video. Dx dt, we know, is just x prime of t. And let's just rearrange that. Dx is x prime of t dt. And look, that's exactly what we have here. So x prime of t dt just ends up being dx. And again, we can just repeat that with the y part. This ends up just being dy. So actually, we can simplify this. And what we end up having is that if we're dotting these two vector functions, f and dr, which is what we're doing when we're doing that integral, this is really dotting the functions p and q with just these two differentials, dx and dy. And why is this useful? Well, consider what the dot product of these two actually works out to be. It ends up being the function p dx, and adding to that, the function q dy. And that should look very familiar to you, because this is exactly what we did in an example previously when we were looking at scalar fields. This is a combination of coordinates. So what do I mean? Well, here's an alternate form of looking at a line integral of a vector field. Again, we have our f and dr, but now we can think about this actually as the line integral of p dx plus q dy. And why is this useful? Well, what is this? This is exactly a combination of coordinates. And not only is it a combination, this is no longer really a vector field. This is for a scalar field. And so if we just simply transform a vector field into a form like this, we can use all the different techniques we talked about previously about how to compute, in this case, a combination of coordinates. And so then it becomes very similar to what we talked about before. Now in the next video, as I mentioned earlier, we're going to be looking at an example where we are trying to find the work done by a force, which is a very common example.